Hi everyone, thanks for joining us today.
It does sound sophisticated.
Sophisticated, yeah.
With the ACE community for 3 years now.
Actually outlined everything.
Something that we find in the society.
First, talk about the problems that you're trying to solve.
Hi everyone, thanks for joining us today. We are with you with another episode of Deep Random Talks. In this stream, we talk about NLP topics with NLP researchers and people who are building NLP products in the industry. And today we are fortunate to have Bai with us. He has just wrapped up his PhD at University of Toronto and is moving on to a very exciting role in industry. We'll hear a little about that. But before going into that, Serena, thanks for joining the call again, my awesome co-host. What's new with you? What's happening in your life these days?
Yeah, happy to be back on DRT, I should say. I haven't gone anywhere recently. Not too much is new. I was thinking about how to answer this properly before we started recording. One thing exciting is I have my app Food Shake, and I've actually been able to show it to some friends who aren't vegan. And maybe backing up a bit, the whole idea of Food Shake is translating recipes from non-vegan to vegan. Before, my friends who aren't vegan, they didn't really care about it, but I added a bit of a design to it, which may not be the right way to approach things, but it's at least been able to get it in the hands of my friends who will now take me a little bit more seriously. So I have more people to test out the validity of the recipe conversion. So I'm excited to get that feedback.
That's awesome. It's always fun to get more feedback about something you're building and, learn from those interactions. All right, Bai, welcome to our show. So tell us a little about yourself and, let's get started there.
Yeah, thanks for having me. So a bit about myself. I just completed my PhD at the University of Toronto, and my thesis was on linguistic theory and natural language processing. And now I'm going to work as a machine learning engineer in the industry. And prior to that, I also tried to make a language learning startup using AI to help people find reading materials. So that's a brief summary of myself.
That's fantastic. What are you all drinking today? I'm having some, I think it was lavender tea. It is a sweetened lavender tea. It's a bit of sugar, I think, in it.
You've always got great teas, Amir. I have English breakfast tea with some almond milk in it.
I'm drinking some sparkling water.
Is that AHA or bubbly?
It's called bubbly. So yeah.
Okay.
No sponsorship, just what I'm drinking.
Well, AHA's been all over the place. They've been giving away a lot of free products in Toronto.
Oh, really? Wow.
Anyways, so Bai, as you said, you finished your PhD this year in 2022. And one of the papers you wrote during your PhD focused on a study where you essentially fed different linguistics errors into various BERT-style models. And then from there, you were able to explain how the models behave in response to these different errors.
So my research is basically combining linguistic theory with natural language processing. So in NLP, you have all of these models that are kind of black boxes. And my research is on trying to explain what they are doing inside from the view of linguistic theory.
So it sounds like you were trying to take this sort of other valid scientific practice, so linguistics, and apply that to NLP and see how you can leverage what we know in linguistics to better explain these NLP models.
Yeah, exactly. So actually, these are two different disciplines that both study language, but in kind of different ways. So in machine learning, often you treat language as just a sequence of symbols that don't really have that much structure. But linguists, they care a lot more about the structure and all kinds of patterns in language and analyze them formally. So these two camps don't talk to each other that much. And what my research does is bring together the prior research in both areas to see how they can be combined together.
So is that what you were trying to do at your startup as well, or was that like a completely different adventure?
It was, I think, pretty different. So my research is kind of on explaining how these models work So this is more of a scientific problem of how does models like BERT manage to achieve such great performances on so many tasks, like what kind of linguistic operations is it doing, and then that's not really like a commercial problem that like startups are doing. It's more of a scientific problem. So that was my PhD research.
And explainability in NLP, I have come across it before. I think as many people listening to this probably have. And the perspective seems to be more so from let's look at the attention weights of a model given some sort of input sequence. And then from there, you're able to understand how a model might work. But as you said, with your PhD and this particular paper that you wrote, that we're focusing on, you took that different approach. So you came at it really from a completely different angle from the linguistic side.
Mm-hmm. Yeah, examining attention weights is definitely a common method. I guess problem with that kind of approaches is that there's so much going on in attention, and then it's hard to draw much conclusions that's really definitive. And there's like so many ways you can probe it, and that's definitely an issue in most linguistic probing research as well. Like how do you probe, and like does that affect the results?
Right, and there's so many different ways to compute attention. So I imagine it can be confusing to really understand how is the model working, and based on the different method you use for attention, you could come to a different conclusion potentially.
Yeah, so like I think the most reliable probes are the ones that are examine the behavior. So given like input, what outputs does the model do, and is it correct, and in what circumstances is the output correct, and that relies less on like examining the internals of the model, and there's like less different ways, degrees of freedom that you can do the probing.
So let's take a step back, though. I believe in when we were talking in our coordination call, you said that was not the topic of your master's project. Like then you were working on some medical NLP project where you were trying to detect dementia based on text. Is that do I remember correctly?
Yeah, so actually my master's project was in the same research lab, but it was on quite a different topic. My master's was on detecting dementia through speech. So the patient would tell a story, and then we will use natural language processing to assess whether you have early signs of cognitive impairment. So that was more like of medical domain and something like more real life and practical. Whereas my PhD research is a lot more theoretical and using like linguistic theory to examine how these models work. So quite a different area.
Yeah. So was there like what was the inspiration to move from that topic to looking at linguistics and its impact or like interaction rather with the more modern statistical, machine learning based NLP methods that we use these days? What was there a specific event that inspired that, or was this in the back of your head all the time and you eventually acted on it? Like, what was the thinking process?
I think one reason that it's it's a little bit more fun because like the what you do is more is cleaner. Like you don't have to rely on so much engineering and messy real world data sets as much, and instead you get these linguistic theories, and then these are a lot cleaner. You can generate data based on these theories, and then there's a lot more formalism instead of dealing with real world data where you never know if your assumptions are correct or not.
Yeah, you mentioned when we chatted in our coordination call that you met some collaborators that through meeting them that really sparked, I would say maybe sparked your interest, but also was an external force in your decision to move from applying NLP to dementia detection to then applying linguistics methods to NLP. So yeah, can you tell us more about the collaborators you met and how that moved you to this problem space?
Yeah, so that was an interesting process. So at my university, you need to form a committee of 3 professors to basically guide you through your PhD. And I always knew I wanted to do something related to linguistics. So I was looking for people in the linguistics faculty that would work with me. And initially, my project was more on speech and phonology. But then the first person that I found who wanted to work with me was more of did more of semantics. So then for the rest of my PhD, I switched gears to work on semantic problems and combining that with NLP models.
Definitely, I see your point about, going a little deeper under the hood and probably, using some mechanism that is more, as you said, formulated and formal to look at, how it behaves and, what is really going on behind it. So to clarify a little, so you said at the beginning you were taking a bit of a speech approach to this problem. Like, was that your assumption that that's the best place that you can probe for explainability of the performance?
Yeah, so I worked on a few different projects before finding the right fit. Like initially, I was trying to make the machine learn like the phonemes of a language through speech. That was one of the first projects I did in my PhD, and that was okay. And I published a workshop paper from that. But I think that problem was just not an important enough problem, and I didn't have a sense of which problems are important and which ones are not as an early PhD student. So one of the ways that community really helped me was like decide which problems are worth working on, and then that turned out to be problems related to like syntax and semantics.
So in terms of definitions, so you worked on phonological elements of language, and that's what the paper that you published, that was a workshop paper, right? Okay. And phonological, I'm looking at the definition of it. So the definition is phonological is relating to the system of contrastive relationships among the speech sounds that constitute the fundamental concepts of a language. So what is an example of a phonological element of a language?
Yeah, so phonemes are like distinctive parts of a language that you can say. So like when you say ma, like ma and are kind of phonemes. And then one of my projects was like detecting the set of phonemes in a language using audio. Yeah, but then when we work with text, usually we don't care about phonology as much because we're handed all the text and then we have all the words, and then we're more concerned with the meaning of words and how they fit together. So that would be syntax.
Okay, so it sounds like you went from sort of more of a atomic study to a study a bit more high level that really captures like the entire language. So yeah, you mentioned you worked on, your next work was focused on semantics and syntax and around creating semantic and syntactic embeddings. I think we should also define semantics and syntax.
Yeah, so these two are kind of very closely connected. So syntax is about the structure of language, like what kind of sentences are permissible in the language. For example, like the happy boy is like a noun phrase, but then like you can say like boy the happy, that would be not a valid phrase in English. So that's about the structure of the language would be syntax. And then semantics is like taking the structure and then figuring out what it means. What does this sentence mean when you have these words arranged in these ways? And then there's a lot of connections between these two because like how does the form of a sentence affect how it means? That's the connection between syntax and semantics.
Right. And an example you gave in your paper around a semantic anomaly. Well, first of all, something that would be correct syntactically would be the boy ate the sandwich. So that's a completely fine sentence in English. But if you said the house ate the sandwich, that's syntactically correct, but semantically it doesn't make any sense.
Yeah, exactly. Like the structure of the sentence makes sense. Like you have the noun and then the verb and then the and then the object of the verb. Like that makes sense. But then when you put it together, like a house cannot eat a sandwich. Right? That doesn't make sense. So that's kind of what I was examining, like the difference between syntactic errors and semantic errors.
And if I remember correctly, your first attempt was that you wanted to grab an embedding like bird and sort of disentangle the components, the parts that represented the syntactics of the language and the semantics of the language. Tell us, what happened there.
Yeah, so that was an interesting attempt. So from the beginning, we knew that we wanted to somehow investigate the difference between syntax and semantics in these language models like BERT. And then the first thing we tried was, can we disentangle the embeddings into like syntactic component and a semantic component? Because you see, like BERT has these 700 dimensional embeddings, and they contain a lot of different information. Some of it is like, what does the word mean? And some of them is like, what does the rest of the sentence mean? And then can we like disentangle them into multiple like sub embeddings? So that was what we tried at first. But then it turned out that there are like linguistic assumptions that make this whole like attempt not really make sense linguistically. So the assumption is that you can disentangle them, so you can change the syntax of a sentence without affecting what it means. But really, like, that's really not something that that is true in language, because whenever you change a sentence, for example, when you change an active sentence into a passive sentence, like, it doesn't mean exactly the same thing. So the semantics will always change along with it.
So if I want to regurgitate what you said, like, my understanding is that from a linguistics point of view, there is too much coupling between the syntax and semantics of a sentence. So even separating them from a linguistic point of view will be a challenging task, let alone figuring out how to do that for a vector. Is that roughly the conclusion there?
Yeah, so to give you an example, you can have a sentence like, the boy ate the sandwich, and then you can have the passive version of the sentence, like, the sandwich was eaten by the boy. And on the surface, it looks like it means the same semantics, but there's like linguistic differences as well. Like, one emphasizes the boy being the agent, and then one of them emphasizes the sandwich being like the main focus of the sentence, and then the boy would be less important. So there's always differences when you rearrange sentences in this way.
So presumably you tried this and you found that the models you were using, so BERT, I assume, wasn't, you mentioned you were using BERT. So the model wasn't able to do this disentangling exercise. So then you moved on to looking at how you can inject linguistic errors into BERT models and then understand how the models behave by looking at the layers of the model. And how did you move from the embedding approach to sort of that explainability approach that you later published your paper on?
Yeah, so the problem was not even that the model cannot do this task. It's even worse than that. Is that the task itself does not make sense. Like, what does it mean to disentangle these embeddings, and how do you even know if you succeeded or not? And that was very difficult to define and to evaluate. So instead of doing that, what we decided on doing instead was like looking at sentences that had different types of errors, either like syntactic errors or semantic errors, and then seeing whether these errors will show up differently in the internals of these language models, like BERT.
And if I remember correctly, you specifically injected 3 types of errors. So there's syntactic errors, semantic errors, and you said common sense errors. So can you explain the third one? What does that mean, and how is that different from the other 2?
Yeah, so a common sense error is like a sentence that is has no problems with it, but is just something that is unusual and less likely to be said in real life than the reverse. So example would be like the waitress served the customer, or the customer served the waitress. And normally the customer does not serve the waitress. So that would be a common sense type of anomaly.
Right, and the methodology used was, grab a trained model, feed it sentences, and look at the distribution in each of the layers. Each of the layers of an architecture like BERT, sort of like fit it to Gaussian distributions, and then feed it in correct sentences and see how these distributions change. Right. So one question that occurs to me as I'm saying this again is, this is a distribution of what? Like, what are we looking at? Is a distribution of the weights in that particular layer?
Yeah, so I'll explain what we did technically. So we took these pre-trained models. At the time, the most popular ones were like BERT, Roberta, and XLNet, and these are models that you feed them a sentence, and they go through a bunch of layers. I think 12 layers, and then you would try to predict masked token, something like that. And the issue with this is that it can predict like which token is likely to fill the mask position, but it can't really tell you why. Or like there could be different reasons that this token does not work in this position. And what we did was we looked at the internal layers of these models and then see at which layer does the token become out of distribution. So then then we have some information about different types of errors, because depending on what layer does the token become out of distribution, then that tells us some information about what's going on.
So as a clarification question, so you took these pre-trained models and then you fed through these different sentences with linguistic errors, and it sounds like you were sort of fine-tuning, so you had to learn these new embeddings and then look at the distribution. Is that right? Or you were sort of querying the model and not doing any fine-tuning on top of it?
So we didn't do any fine tuning actually. What we did was we took a corpus of correct English text to learn like what are the embeddings at each layer supposed to look like, and then given a new sentence, we can generate new embeddings and then see whether this new embedding is in distribution or out of the distribution compared to the correct language embeddings.
Got it. And then presumably the difference between the, I guess, output embedding as a result of the erroneous sentence and comparing that to the embeddings in the distribution from the correct corpus, that difference, that's the surprise that you mentioned.
Yeah, so we fitted two sentences that are very similar. One is correct and one is incorrect. So you have a sentence like the boy ate the sandwich and the house ate the sandwich. And then the only difference is the token house versus boy. And then we would look at the difference between the surprisal of the boy token in this distribution versus the house token. And this would give you a surprisal score of how surprising is this sentence compared to the correct one.
And does the size of this surprise factor, or did you measure the size at all? And then does the size represent anything significant?
Yeah, so we compared the size of the surprisal between layers, like from layer 1, 2, 3 up to layer 12. And then this gives us a kind of shape of at what layer does the surprisal start to pick up. And then that gives us information about how the model is processing the sentence as it goes through the layers.
So is there any, like, did you explore any sort of correlation between how bad the error is? Like, for example, the boy ate the sandwich versus the dog ate the sandwich versus the house ate the sandwich, right? So there could be some gray area things that, dogs don't usually eat sandwiches, but it's not completely crazy either. Like, is that something that you explored at all?
Not in this work, but it's an interesting question, because definitely there are degrees of like ungrammaticality, but then the challenge is like how do you know the degree, and like people might disagree on how bad is this sentence. So in this way, we just considered a correct versus incorrect sentence.
Right. And when you say out of distribution, what was the, technical, like, was it 2 sigma out of, was it 2 sigma away from the center that you expected or something like that? Is that, like, when you say it's a statistical metric of being an outlier or anomaly was what you were looking for?
Yeah, so it's the degree of being out of distribution. So what we did was we trained a Gaussian model, like multivariate Gaussian, on the set of embeddings that are correct, and then we measure like the probability density function of the new embedding on this trained Gaussian, and then this gives us a score of how surprising is it.
And I think it's really interesting what you mentioned, how you were able to look at the different, where the surprise shows up in different layers of the model. and thinking about the three different kinds of linguistic errors you used. So there were syntactic anomalies, semantic anomalies, and common sense anomalies. And I was thinking about this before we started talking and trying to sort of reason about it and think, where would it make sense for these errors or for the surprise to show up in the model? So at first I was thinking that common sense errors would probably be the easiest, let's say, for a model to understand, because to me as a human, that sort of makes the most sense. If I hear someone say something and it doesn't make sense, it's usually a common sense error. At least that's when I would personally feel the most surprised. But then in terms of a language's ability or a model's ability to encode language, I would actually guess that syntactic errors would show up earlier layers, in that the model is better able to detect any errors there. Then I would guess that semantic errors would show up a bit later. And I would guess that common sense errors might show up all the way at the end. So what did you actually find? Which errors were the easiest, I would say, for the model to pick up on, or they would be surprised the quickest?
Yeah, that's basically what we found. We found that the syntactic errors didn't take very long to be picked up. So stuff like subject-verb agreement or determiner-noun agreement, those tend to be pretty easy for the model to pick up. And then the semantic errors took more layers. So near the end of the model, it will start to become out of distribution when you have a semantic error. And then when you have a common sense error, at least our Gaussian method was not able to pick up any kind of anomaly. But then at the end, when the model is asked to make the prediction, it's able to generate the prediction correctly most of the time. It's just that it did not appear out of distribution in our probing method.
That's interesting. So as a conclusion to that, would you say that these large language models are better able to encode the syntax of a language rather than the semantics? Is that a fair statement?
Yeah, I think it takes less processing to detect like syntactic errors, just because there's less level of language that you need to understand. Like all you have to do is find the subject and the verb, and then see if they have the matching agreement or not, and then that's like a relatively small amount of processing or understanding needed to perform that.
Yeah, that's very interesting. So if I was an NLP scientist in industry, and if I knew I had a problem I wanted to solve that relied heavily on syntax, then I could guess that I would need less processing power than if I'm trying to solve some common sense language problem.
Yeah, definitely. I would say that that's true. Like syntax problems are like easy to find, and like even models without deep learning can find like these kind of errors pretty reliably.
And did you see any difference between different? I think you said that you tried 3 different models. Did you see any difference in these different models, and do you have an intuition for what explains the difference?
Yeah, so we found that Roberta had like more of a difference between like syntax and semantic anomalies compared to BERT. And I think the reason is just that it's a bigger model that's trained with more data, so it can do most tasks better than BERT, and that was kind of expected.
Yeah, interesting. So I guess, one thing that I wanted to discuss was what's the consequence of these observations, and what Serena pointed out, and you elaborated on is definitely very interesting. Language models are better at learning syntax because that's a more limited space, and with enough examples you can just follow. Okay, this is the general pattern that I see in all of these, and I can see that happening. But we started this conversation by saying that you wanted to use linguistics to provide exploitability. So, how is this change in distribution? How is it providing exploitability to an end user? And what are some of the ways that you think people can use the outcome of your research?
Yeah, there's actually kind of two different questions. I can answer it from a scientific or like a practical way. So from the scientific perspective, like this result is interesting because it shows that there is kind of a difference between syntax and semantics that's visible to the language models. So these language models, they're only trained on a lot of data, and they see a bunch of tokens, but they don't know they don't have any connection of a word's meaning to anything in the real world, and despite that, it can still learn that there's some kind of difference between semantic anomalies and syntactic anomalies. So that is really interesting. And then on a different note, like how is this useful for real life? I think one way that this research could be useful is a grammatical error detection in low resource languages. So we have a way that to detect like syntactic versus non-syntactic errors without needing to have a lot of annotated data. So that could be useful if you're trying to train a model in some language that you don't have a lot of annotated data and you only have like just raw text.
Can you expand that a bit, because I sort of get it but not quite. So you're saying, given that BERT is trained on English, for example, and we know its properties in terms of, okay, it understands the syntax better, and then understands the semantics less good, but now we want to train on a new language that we don't have a lot of annotated data. So like how does this observation that we just talked about in the past half an hour or so help a researcher in that, or a practitioner in that low resource language to train their models better?
So first of all, you can train a large language model on just data. You don't need any annotated data. So like if you have some relatively low resource language, you still have a lot of data of like people writing in that language. But then now I'm saying I can detect like which errors are syntactic in nature using just this corpus of data without you having to annotate. Here's a syntactic error and here's like a non-syntactic error. And I think that could be really useful.
Yeah, so it sounds like this understanding, it has a very valid, or the explainability, I should say, that you worked on has a very valid application in detecting errors. And I'm wondering, can you see any applications? I'm really just curious. Can you see any applications in sort of the prediction side?
What do you mean by that? Like,
I guess I'm wondering with this knowledge that these large language models are better able to handle and model syntax. Can that help us at all beyond detecting grammatical errors? Could it help us construct models that are better able to generate text? Kind of just throwing it out there to see what you think.
Yeah, I think so. Like there could be a lot of applications of like being able to differentiate types of errors. So, for example, maybe you want to construct a system that that the user is allowed to say like very unexpected things, but you expect that they will speak in a way that's syntactically correct, and how to allow that, like maybe in a speech recognition system. Then you want to somehow differentiate if the error is syntactic or semantic, because then you still want the semantic error to go through.
Yeah, it's very interesting. And as always, I'm thinking, how can I apply this to my work, which focuses more on numbers, I would say, and time series of different financial data points. I'm not sure it is quite applicable, but let me know if you do have ideas. Maybe we can chat later too.
Yeah, sure. Yeah, I think this is more of like dealing with linguistic structures. So if your data is not linguistic, then you'll probably use different like anomaly detection methods.
Yeah, one question that I'm inspired to ask now is if this observation makes any, essentially inspires us to do training in a different way. Because, a lot of the time, the reason that large language models exist is that, we need to throw tons of data at them, because we need to essentially denoise all of the possible noise that exists, including, anomalies like what we are talking about, to the point that the model just learns the more stable patterns and then can essentially perform based on those patterns that it learns outside of all the noise that it is exposed to. So with this observation, because a lot of the time, people talk about explainability in the context of trust and ethics and et cetera, but really, the most, I think, fundamental use case for explainability is just making our pipelines better, right? Like, because if we know how something is behaving, then we can go back and re-engineer the architecture, re-engineer the training processes, etc. Is that like, did you think about that at all? And you have some ideas around how, this knowledge can affect, training large language models that don't require as much data, for example, or any other type of improvement?
Yeah, that's definitely one application of linguistic probing. I think it's less applicable for this particular project, but in other linguistic projects, they have some kind of test suite of different cases that are kind of difficult for models to handle. For example, subject-verb agreement when there's like a lot of distracting things in between, and then this serves like as a sort of benchmark where you can see, does the model perform better after you train it in a different way, and then that gives you like a very fine-grained benchmark of what the model is good at handling and what needs to be improved. So that's one way that linguistics is contributing to deep learning research.
Yeah, I have a follow-up thought to Amir's question, and Bai, you might have just answered that when you said that there's research in using different training tasks. I'm thinking about with BERT, for example, there's these two pre-training tasks. So as you mentioned, predicting mask tokens and then next sentence prediction. And those two tasks, and this also goes back to Amir's point that if there's more instances to learn the syntax of a language, I'm wondering, would it be possible to come up with maybe a third pre-training exercise that, focuses specifically on learning common sense or learning semantics? I'm not sure if any researchers have tried adding additional pre-training tasks, but I'd be really interested to read any of those papers if they have.
Yeah, I think there are a bunch of research that looks at like how do you pre-train the model, and then how does that affect like how the model performs on various types of linguistic tasks, and that's one direction of research. But I think practically it's probably not going to be that useful, because in practice you just want to get as much data as possible and train as large of a model as possible, and that always does better than like not using more data. So. That's the reality of language model training.
Yeah, and a final thought now that you made me think of this. So it seems like, and again, correct me if I'm wrong, because I am not an NLP practitioner currently. So it seems like the training data we're using, we're sort of passing through valid examples of language. Have there been, or is there any research that you know of or you can think of where you would, I mean, similar to yours, purposely pass through invalid examples of language, but then possibly taking it a step further from your work, actually learning something from that?
I'm not sure what would be the purpose of passing like invalid language, but I've seen research that like controls what types of language that you use in the training data, and then, for example, if you control the input so that it never sees a particular linguistic structure, can the model infer that this structure exists by piecing together other sentences, and then that kind of tests the model's ability to generalize to like unseen types of structures.
Got it. It's very interesting. It's been very thought-provoking for me.
Definitely. So we are almost ready to wrap up. This was a very interesting conversation, and I think for those who are interested in NLP, this is definitely a paper that they should pick up and read more carefully. Of course, we didn't go in a lot of the technical details, but those are written in a paper, and you can take a look at them. But Serena and Bai, what's the verdict? We talked about this topic for the past half an hour or so. But what do you want people to take away from this, especially if if there was something that wasn't quite obvious to you when for Serena before we had this conversation, but for why before you did this research?
Yeah, on my end, I would say for researchers, not just in NLP, I would say be open to applying different scientific methods to your machine learning. You don't necessarily have to only use machine learning methods, and thinking about leaning on other scientific research that's also very advanced could be beneficial, like what Bai did.
Yeah, for me, I think there's a lot of room for linguistics to contribute to deep learning research, because like linguistics, they have looked at probing methods that are similar to what I did for many decades, and then probing in deep learning is kind of recent, and then there's a lot of ways to kind of combine these two schools of thought together to generate new research that's really interesting.
Yeah, definitely. So what I'm excited to see is, being a physicist, I like that a structured, systematic approach to, modeling and solving problems, which is very different and took me a minute to wrap my head around when I started doing machine learning. Because, in some cases, we are doing things relatively empirical and to some extent brute force, without actually knowing what is happening. Just throw a bunch of things at it and somehow it works. We do have some understanding of it, but as both Serena and Bai said, completely ignoring the domain knowledge is usually going to be very inefficient at the very least, because a lot of the time, the reason that those areas exist is that they work. Like they might not work with the to the extent that we want and to the scale that we want, and they might be heuristic based and whatever else, but ultimately there's a reason that they exist. And I'm excited to see more scientific, logical, heuristic based methods like linguistic, like physics, like chemistry, etc., to interplay with machine learning, because that will make machine learning better as well. In addition to the industry applications that we will have for all of these. So thank you so much for listening to us today. I hope you learned something, got inspired to look up some interesting concepts and papers. We will put Bai's paper along with a few other resources whenever we publish this video as well. So you're in for a treat to learn from that. Thank you so much, and hope to see you next week.